Everything is clear? Okay, so I'll try to finish a bit earlier today. That's nice. I'm also getting hungry. So the problem arises in different applications. There is a previous work, which here is just mentioned briefly, but now we want to describe it. So earlier, methods based on neural network, which I mentioned, Bayesian approaches. We use a common prior, which explains how the tasks are generated, right? Online learning approaches. I think Mark Webster will like this the most. So the data are received in an online function, and you want to make predictions time after time. And also there are related areas of research outside machine learning where these problems have been studied. So conjoint analysis, longitudinal data analysis, similar-weighted regression is apparently an important area in econometrics, functional data analysis, and I think there are others. Right. So there was a question, in fact, during the break, which is interesting, about taxpayers. So each task is one person, and you want to predict based on income and other variables if the declared task is correct. Right? So this you could treat as just one regression problem, or you could try to stratify this problem across different people or across different years. So the notion of what the task is a bit arbitrary, right? But so if you like, is a way to put prior knowledge also in your problem, which so you. I will go back to this because it's very important problem, right? Because the problem of learning, so you have an input and you have a task. The task. So you can also see all this stuff as learning just one function, which in a larger input space, where the first component of the input of the standard input is just the task index, and the remaining components are the feature of the product. Right? So thinking of the user model. In this extended input space, the function will be nonlinear, right? Because your model is that each task is linear, right? But overall, it will not be a linear function. So I will go back to that. But you could stratify your problem in a different way. So this, again, I will say more. So what I want to describe in the remaining. So if you agree, I will continue until 4:30, then I will stop. Optimistically. Okay. So we can stop a bit earlier for the last lecture. This is my. I have to meet a faculty candidate, so I need to recover. So, we work in a high-dimensional setting. Each task is a high-dimensional vector because the input has many variables. One question which I described, so what is one important question? What is the multitask counterpart of smoothness and sparsity assumption, which are used in, say, linear regression or nonlinear regression, like for a single task? This is what you have seen in the course. Methods, the lasso method that I described today last week. Other methods. So all these methods make an assumption about the underlying function. The underlying function is smooth, right? In the sense that there is a kernel which models smoothness. So only low frequency components are important. Or the underlying function is sparse, as we described in the lasso method. How do you extend this assumption to multiple tasks? Right? I'll mention a little bit about statistical estimation, but very briefly, and also describe how we solve this problem. Right, so, well, optimization methods. Right. So, right. So this was based on the lecture, so there are quite a few self-references, which I apologize. So this is actually some methods that was studied with these people. So the first natural assumption is to consider a quadratic regularizer. Right? So the objective function is a quadratic function of this type. So it's W transpose E W. Now W is the concatenation of all the regression vectors. So it's a very long vector. Before I said it's a matrix, now I regard it as a concatenation of all the columns of this matrix of all the tasks. So you need to adjust the notation depending on your need. So, and the matrix E, this huge matrix, is Poisson semi-definite, so that you have a convex regularizer. Right. Right. So this is very general, depending on which matrix E you choose. And, but so here I discuss only one example, which is this one. So it's very simple. So the regularizer is the sum of the square norm of each task, and then it's times a parameter, which I now discuss its role, times the variance, not before, right? Okay. So the first term is the sum of the two norm, and the second term times this parameter is the variance of the different tasks. So we will solve this problem for this choice of the regularizer, and the idea is that, right, so this parameter gamma is between 0 and 1. If it is equal to 1, this term is 0, and the tasks are learned independently. So they are ridge regression. Each task is a ridge regression. So here you put some other loss function, like the hinge loss, like is this one, right, for classification. You do independent subvector machines. If you do logistic loss, you do independent. Okay, so if the parameter gamma is equal to 1, you do independent regularized linear models. On the other hand, if the parameter gamma is equal to 0, right, this term, this ratio explodes, right? And since you minimize here, what will happen is that all the vector WT will be forced to be equal to each other. So you will learn only one function, only one model, right? So this is the opposite situation, right? So in that case, the tasks are completely dependent. They are the same. So all the people give the same response to problems. So you see, this is a little model which is very simple, which is this very specific special case of a quadratic regularizer. Already captures something quite interesting, right? Capture kind of interpolate between two very different models. Clearly, the first model, gamma equal to 1, it's a more complex model because you need to learn the parameter of each of the tasks, right? And this is a model which eventually, if you have enough data, should work well, right? The second model is very simple because it forces all the parameters to be identical, so you only have to learn one parameter vector. So the second model will be for sure beneficial when you have very small sample size. Hopefully, something in between will work. So you can analyze, and this is not discussed here, like the bias variance, the composition, or do a statistical analysis of this kind of model. And I think it will be an interesting exercise, or something which is not written in any research paper as far as I know, but because people kind of know it, but it would still be interesting to spell it out, so to speak. But what will happen is what I said. So, this parameter gamma will, the larger it is, the more complex the model. Right? So this is just a simple example. But so you could choose other matrices E. Fine. So maybe you have some prior knowledge and you have a way to choose the matrix E, which here is an example. But there is another point of view that you might follow to solve all these tasks together. And the other point of view is what I mentioned before, is that you can see multitask learning as learning a single function on a larger domain, right? So you take X as your vector, and T, right, which is your index, and then you have Ft of X, right? So it's not a matter of notation, but we can also write this as capital F of X comma T. So I regard these as only one function, right? And here, so the other point of view, following these, so the other representation of following this point of view is this one. You say that this function, right, this Ft of X, regarded as a single function, you write it in terms of a feature map. So feature maps we have in, so this describes the moral of this slide is that this is just a kernel method, okay, with a special feature map, which basically is a linear transformation of the input which is task dependent. So this matrix is BT is one for each different task, right? And if you choose these matrices, so there are autoparameters as you see there, because each matrix is autoparameter. These are fixed a priori, they are part of your prior knowledge. Very much like the kernel function can be seen as a way to model prior knowledge, right? And right. Also in the context of Gaussian processes that maybe you have seen in some other lectures. Have you seen it in unsupervised learning or in graphical models? So these also can be described in that language. Right? So these matrices are prescribed, and now all you have to learn is the weight vector V, right? Right? And it is obvious, it's not written here, that what before I call WT will be, what will be? Will be BT transpose V, right? Yes. Right? But here, if you look at this, so, and what you can show, actually this is mentioned in the next slide, this is completely equivalent to what, to the previous method. We'll go back to that. But if you start from this method, you can see this is a kernel method where you have this multitask kernel, right? So it's this kernel on this extended input space. So it's a kernel of X comma T, comma the other extended input, right? Which has this form. As you see, is bilinear in X, but in T it involves these matrices. So you can use all the methods that we have discussed in the context of kernel methods, or regression, SVMs, with this kernel, and solve the problem. It will be a bit more complicated if you think about it, because in this formalism, right, so here you have a double sum, because you still have data which are stratified across the different tasks, right? So effectively, the number of data points is T times N, right? So it's very large. So this number might be very large because N might be small, but the number of tasks might be very large, right? So you have like 500,000 people, and each sees 20 movies, then suddenly it becomes a very large data set. And in general, if you choose this matrix Bt, some general, so this can be any matrices. In general, this problem cannot be decoupled, right? Unlike the previous problem. So the previous problem is a very special case of this that we will see, in which you can make a change of variable and still solve capital T independent problems, right? So there is an efficient way to solve it. In general, this problem cannot be decoupled, so you need to do a kernel regression with a very big data matrix. Right? So a matrix which is Tn times Tn. So right, so the two problems are equivalent, you can show. This was the previous one, and the proof is not difficult. Here I skip it, but it's kind of intuitive because you make a change of variable. I describe this a bit more detail in the special case of the small variance. So what you can show is that if you fix these feature matrices, B, B1 for Bt, under some assumption that their concatenation is full rank, then if you set the matrix E equal to the inverse of Bt, B transpose B, then the two problems give the same solution. Right? Right, so, and conversely, if you fix the matrix E, and then you take A to be a square root of E, and you set B equal to this equation, then the second problem gives the same solution. So you can show this type of results. So I skip the details, they are in the paper, but this is not very important. Okay? But think of that in this case. So this is the case that we described before, right? So these lines can be read from the bottom. So this was the regularizer that I introduced at first. So it's this trade-off between small L2 norm of each column, of each task, and small variance. You can reinterpret, using the previous proposition, this regularizer, right, as choosing some feature maps, Bt, this matrix is Bt, one per task. Now you apply the result. So what you can verify as an exercise, the underlying idea is very simple. So the underlying idea is that, remember that the vector Wt are equal to Bt transpose this vector V, right? Used to represent the extended, the function in the extended input space, right? Now, what is the idea? The idea is that these matrices Bt transpose are a concatenation of many matrices, where the first one is kind of always the same, no matter what T is. And all the others are zero, except at the Th one is a multiple of the identity. And there is also this parameter. So at the end, what you get is that Wt is equal to some vector V0 times some constant, which is the root of 1 minus gamma, plus the root of gamma times T, times a vector Vt. Right? So the vector V is V0, V transpose is V0 transpose, V1 transpose, V capital T transpose. Right? But the matrix Bt only select V0 and the corresponding Vt. So the idea is really just that the task vector Wt is equal to a common vector plus a task-specific vector. And this parameter gamma, that before here has this clear meaning of pushing more the variance to be 0 or letting it unconstrained, here appears the same fashion. So if the parameter gamma is close to 0, you only care about the common part, right? And this confirms what's happening here. If the parameter gamma is close to 0, you want the variance to be 0, right? And if gamma is equal to 1, you only care about the task-specific part. So you can see that this method, which starts with the quadratic regularizer, is equivalent. And you can see if you do the calculation, it's equivalent to using these feature matrices, which are interpreted as this model of common part plus the task-specific part. Right? So, and you can. So this is just an example that you can do. Many others, right? Either starting from this formalism or from this. Either choosing matrix E or these task-specific feature matrices. So, for example, you can extend these to have like a forest of tasks in which. So here you say everything is similar to each other. Then you can have some hierarchy or something like that. Well, I won't discuss that. So, the second technique which I described is this idea of having common features shared by the task, right? So this is implemented by different type of regularizers. They are very different. They are not quadratic, right? They are based on sparsity. So particularly, they are a form of structure sparsity. And this is what we've already seen. They are this group lasso idea, where so we choose this regularizer. Now, sorry, before I go that, so here, which we also like to look at the matrix. Those columns are the task regression vectors. And look at as the rows of this matrix as each being indexed by one of the variables, one of the features, right? Okay, so all these vectors are, say, one-dimensional, and each component refers to one specific attributes, right? So it could be that you describe the computers by 20 variables, and right, so. And here, so what you require that only few of these variables are important, and for that reason you take. It seems appropriate to take the sum of the two norms of the rows of this matrix. Right, so this Wj is the jth row of the matrix again, right? And here you like the matrix of tasks to have this row sparse structure. Right? So here there are only two rows, only two variables which matter in the sense that most of the tasks use either one of the two features or both. Right? So this can be seen as a special case of the group lasso, which discussed before, right? In the sense that you have a big vector, right, the matrix, and the groups are the first group are all the elements which are in the first row, the second group, second row, and so on. So, right? Does it make sense? So this it's a different notation than the one we use in the group lasso, but in the group lasso we use this notation. So we have the sum. So we'll go something like that. WJN, right? And from 1 to n. That was the notation we were using there. So you choose n equal to d, and you choose JL JL equal to so it will be L1 LT, right? Because the components of W have two indexes, right? So the first is the row, the second is the column. You fix the row. Right. This also was a little bit of a repetition from the previous slide. This is a kind of a graphical example where you see that indeed this kind of regularizer favors, right, this situation. So as opposed to the L1 norm. So this. So one possibility would be to take the L1 norm of the matrix elements, which favors sparsity but with no prescribed structure. And the second one is what we described, and the third one is the combinatorial regularizer, which is non-convex. Right? And so these two are convex because they are norms. But the number of rows, right? If you want your regularizer to kind of mimic the first one, right? And to some extent it does. Right? Of course, it's not the same. You can show that this is something that we didn't describe. That you can show that these regularizers are the best approximation among the convex one to the combinatorial regularizers. Right? So you can show that the L1 norm is the best approximation of the cardinality in a certain sense. And here, likewise, you can show that this sum of L2 row norms is the best approximation of this type of combinatorial regularizer. So this is discussed in papers, and I can tell you more if you are interested. So this idea of what's called forgot. So you use a Fenchel duality. You need to compute the dual of a function and then the dual of the dual. Right? That is convex. So you take a function which is non-convex, is a cardinality. So you compute the Fenchel dual of this function, and it will be convex by construction. You compute the dual of this dual, if you are able, that will be the convex approximation of the original function. So it works like that. But we haven't discussed what so this is also called the Lejean transformation. It's Fenchel. We might discuss it tomorrow this time. So it's a bit behind. This part is also here because I was present in this meeting, but it's a little bit of a, how do you say, intermezzo. I think it's an English adapted word, parentheses. So it's very interesting to study the statistical property of all these methods, right? And here, this is just to give you some flavor of what that means and which type of results people are after. First, you assume a model. Like in statistics, you need to start from a model, right? Also machine learning. But here you spell it out precisely. So you assume that the data generated by the linear model, and you make some assumption about the noise. So this epsilon ti is the noise that you add. And you assume that they are IID Gaussian, some variance, sigma squared. And then you make an assumption which kind of motivates using this structure sparsity. And the assumption is that this set J of W is the set of common variables shared by the task. So it's a set of all the indexes J, which goes from 1 to D, so they are the rows, right, in the matrix, such that the corresponding row is non-zero, right? So this is what this equation means, right? This equation means that the row J of the matrix has at least one element different from zero, right? Now you assume that the cardinality of this set is less or equal than S. So there are at most S non-zero rows in the model, right? So this W is the true model. Then you make another assumption, which is assumption that the uncorrelation between the different variables. So this is a strong assumption. These are all strong assumptions because we don't know if these things are true. So all this stuff, it is not very useful in practice, but it's very useful as for understanding, I would say, right? So you understand that at least in theory, these methods can be much better than others in theory. So if the assumptions are correct. So the last assumption is the assumption of uncorrelation between the different variables. So you take the variable k and the variable j. So these are two different components, right? So xti is the input, is the hive input for the task t, and this j means the component j of this vector, right? So this can be seen as an empirical, perhaps this is the empirical correlation between the variable j and the variable k, right? For task t, as you can see. So this is, right? So this is exactly the assuming the zero mean, right, of this. This is the empirical correlation between the variable j and k, right? Or the second moment, if you like. Now you assume that for every task t, this is not too high, right? And this is controlled by this parameter rho, right? So the larger this parameter rho, the closer to 1, the less correlated the variables. But this is important because if the variables are correlated, it is more difficult to, so your sparsity assumption becomes kind of vacuous, right? Because there is redundancy in the way you describe your problem. So the question that you want to ask is, can we say something about the quality of the estimation? So this is the average error, right? So W hat is the solution of this previous problem, and WT is the model. Or can we say something about whether we selected the true, right? This is a variable selection, model selection question. Is it true that the set of non-zero rows in the matrix W hat is the same as the true? Right? This is called the sparsity pattern, if you like. So this question can be answered with statistical tools, and for example, the type of result that you obtain for the first question is of this type. Right, so you obtain that under the assumption, if you choose the regularization parameter in a certain way, remember the regularization parameter appears here in front of the sum of the L2 norm of the electrons. So you choose it proportional to the noise level. So the more noise you have, the more you have to regularize. Seems intuitive. And the larger the sample size per task and the number of tasks, the less you regularize because you have more knowledge. So it also seems to make sense. The larger the dimensionality, the more you regularize, right? And there is also T here. Now, if you choose the relation parameter by this equation, so when A is less or greater than 4, then you obtain an upper bound on the estimation error of your method, right? Where you see, this is also important, this will be read. The less correlated the variables, the better the estimation. Remember, the rho is between 0 and 1. And then you see that the sparser the model, the better the estimation, because it is S over N. And then there is this nice property that the number of rows, number of variables appears only logarithmically. And this is a typical in all these results of sparse estimation. The number of variables appear only logarithmically. So if you have only, for the lasso, the result will look similar to this, but it will be more like S over N, and then it will be log d or root log d, because I don't remember. Okay. But so this bound is good also if this d is much larger than the sample size. But in this specific case of structure sparsity of multitask learning, if t is large, this term disappears, right? So the benefit of this method, the more tasks you have, the easier it is to find what is in common. This also is kind of nice, so it's kind of intuitive. Right? Since you assume that only few variables are important, the more tasks you have, the easier it is to find them. So that's kind of the result, right? Well, here we speak of finding the regression vectors. Similar results holds for that. And then what you can show is that this is the performance of your method. If instead you use the lasso method, which is right, which will be right, so this one, right, doesn't use any structure, then you cannot get this type of result. So you can show a lower bound. So you can show that the lasso method, under some very pathological case, although these things are a little bit borderline, because you always, they are kind of worse analysis. So for a certain configuration of the problem, which satisfies the assumption that you made, the performance is greater or equal, so there is S over N and there is a log of D, which is nice, but you cannot get rid of T, so there is a log of dt. So, whereas here, as T grows, so the performance can be much worse. If you were doing least squares, the performance would be even worse, because it would be something like so it would be something like d over n, perhaps the root of d over n. So there is no sparsity which appears there, right? Because sorry, the ridge regression. The ridge regression does not favor sparsities. It favors different type of favors small values kind of uniformly across all the components. Right? So these are the type of results. Now the last method is based on what is called spectral regularization, right? So here the idea is that, so you want to favor, for example, low rank matrix W, or something which involves property of the spectrum of the matrix, the singular values. So the idea that before there were few common variables, here you want to say that there are few common features, which this means that you also want to find directions, right? Few directions which are important in the task. The columns of W are in a low-dimensional subspace. This is the assumption, the geometric assumption. And this is implemented by requiring the matrix W to be of low rank. Right? Because low rank means that each column is a linear combination of few basis vectors. This time, real basis vectors. Right? So, and this also is a very rich stuff. Right, so this is one way to do it that we did with some colleagues. Is that we do exactly what I described before, but in addition we introduce this matrix U, which is an orthogonal matrix, which we put in front of the inputs. Right? So if U is equal to the identity, this is exactly the same as the multitask, what do we call it, the structure sparsity, the group lasso, or also we also call it multitask variable selection. If U is an additional parameter in the problem, it is what it is here, but you can show that this problem can be solved, it's tractable. The reason being that this problem is equivalent to a problem in which you directly optimize with respect to the task matrix W as opposed to minimize over U and A. Right? So in this formulation, what before I called W, right? Here I call A, right? And I introduce this additional matrix U. Okay. So if U is the identity, this is exactly the same as this stuff. Right. Okay, so this. So. Right, so if U is the identity, omega S of A is the sum of the L2 of the rows, and this method is the same as the previous one, except that here W I call it A. If I also introduce this additional matrix U, which are required to be orthogonal, right? Here so there is a clear intuition behind the method. So here I search for a basis, U is a basis, right? Such that in this basis, right, there are only few important variables or features, right? So this will be the new input, the x tilde ti. Right? So it's a vector, a d-dimensional vector, because U is an orthogonal matrix, but only few of these new few components of the vector will be important, because the regression vectors AT have this row sparsity assumption, right? Forced by this regularizer, right? Which is the same as the one we discussed before. So it's does it make sense?
Just what the rows are and what the columns are.
That's a good question. It's understandable. It's understandable. Because so when you see this representation with the computer or with the stuff, it's difficult to remember the notation. So it's a good question. You should have asked before, perhaps.
Not before I.
Oh, okay. So let's remember. So, good point. The rows always refer to features or variables. The columns to tasks, right? Okay. So this matrix A is also a task matrix. So there is A1, AT. So there are T columns, which are equal to the number of tasks, and D rows, equal to the number of features that I will learn by the method. Okay? And this I want to have a row sparsity structure. So there will be only few important rows, which means only few important features. The features here are constructed for this matrix U, right, which is D times D, and is an orthogonal matrix, which is part of the learning process. So here I will learn A and U. Right? And A, I will learn it by this sparsity assumption, and U just by this orthogonality assumption, which is so this problem is more complicated than the previous one, because there is this constraint, which is a non-convex constraint. However, so this is what it does. So I think there is an intuition behind. I want to rotate the data so that in the new representation, right, in this new representation, only few components are important across the task. So there is a joint sparsity across the task. But you can make this change of variable and call W U times A, right, which still is a D times T matrix. And what you can see, so here, this will be WT transpose, right? Because you have made this change of variable. Here is WT, and here, right? So because you made this change of variable, so it means that A is equal to U transpose W, right? Because U is orthogonal, you multiply left and right by U transpose and bring it on the other side. So here you have omega S of A, this thing, which become omega S of U transpose W. Right? Here you have get rid of U because you have WT transpose. So the minimum over U, you can bring it up front here. That is what, right? So what is written in this equation. And then what you can show is that you can solve this. You can minimize over U. This is not obvious. You can show that this minimum over U of this function will be a function of W, because U is get rid of, by doing the minimization, will be some function of W. And what you can show is that this function of W is what is called the trace norm of W, which is the sum of the singular values. So, quite a few details missing here, so I'm just telling you the high-level story. But there is a common intuition about this. The initial method is an extension of the previous one, which finds few common directions. The direction need to be found by the method. Okay. Here, in this new formulation, which perhaps I wonder if we so at the end you have this thing, right? So, this is the trace norm, so the sum over J of the singular values of W, right? Also called the trace norm. Not to be confused by the trace of the matrix. So this is it. So if the matrix is symmetric, positive, definite, this is the sum of the eigenvalues. But in general, it's the sum of the singular values. And it is a norm. So this is. This problem, so what it does, it encourages low rank matrices, which means it encourages only few important directions. So a low dimensional representation of the columns of W. Right? So that's the idea, which is repeated here. Right? Just a repetition of what I said. Right. So, any questions? Well, it's a bit technical. I think this stuff 2 years ago I used to teach an advanced topic in machine learning. Then, since I don't teach anymore that course, it will be taught by Arthur Breton and I think David Silver, so they will speak about reinforcement learning, about kernel methods. Not too far from this stuff, so this stuff is also relevant in that area. So, this requires some further reading, but the idea of this lecture that you understand or you are interested, perhaps, not sure, you're triggered, there is some common principle which is intuitive behind this. Yes. So the idea that the tasks are related, and but they can be related in very different ways. So they can be close to each other, like small variance. They can have common sparsity, or something about the spectrum of the matrix plays an important role in relating the task. So the spectrum has a certain decay, or perhaps it is like in this case, it's concentrated on only few. Only few singular values are non-zero, so which means that there is a cutoff, right? So we're not too far from the end. If I skip some part, you want to skip some part, or you want to see all the possible details which are in the slides. I'm very happy to do that. But so you tell me how interested you are, because who wants to see all the details?
Whatever you can manage to make understandable in 20 minutes.
This is a very diplomatic answer. Okay.
That's the best.
Okay. Well, let's say 25 minutes.
25
Okay. Good. So, yeah, I think. So there are 3 further. So no break, because we finish in less than 25. There are a few further issues. So the first one is, how do we solve this problem? I will not describe it, but I give you just some minimal information for further. The second thing, some results, some experimental results, stuff, briefly, and then some extensions, because so this stuff is quite old, maybe 5 years or so, but there have been some development, which I want to briefly mention. So, how we solve these problems? There are different approaches. One is the one we will see tomorrow. So we can solve these problems by solving a sequence of simpler problems in which the error term, right, is just the distance between the matrix of parameters W and some fixed matrix, which changes iteration after iteration. So you solve a sequence of problems of this type, where at each iteration this W0, which is fixed, changes. Like it could be the previous one, pretty much. So it's like it's an extension of gradient descent. It's called proximal gradient methods. And tomorrow we'll discuss it in some detail. These are very popular methods in signal processing and optimization, because they're very simple. Another approach, which actually I studied, they are based on this formula. It's complicated. It's a variational formula, which says that what you want to regularize can be seen as the minimum, infimum, of quadratic functions. So these are quadratic functions. Let's not go there into details. So this is the trace of the function. As you see, is a quadratic in W, and there is this additional parameter D, which here is a completely unmotivated, right? But it's a polysemi-definite matrix, which has not appeared before. And we don't need to worry about that, because I skipped the details. But what you need to know is that if D is fixed, the problem is just the problem of minimizing this thing, right? So what you do this. So you take the minimum over D here, outside, bring it here. So when D is fixed, you have something which is quadratic in W, right? Because you have a loss term, which is quadratic, with the square error. And then you have this stuff, which is quadratic in W. And also this stuff here, before I call it trace, is the same. So is the sum of the quadratic form for each task. So when you fix this is an auxiliary variable D, you can solve the task one by one independently. When you fix the task, you can minimize over D, and you can do it in closed form, or you can show that. Yes, there is a formula for fix W. The minimizing D is essentially the square root of W transpose. So there are a lot of details there. So this is for solving these last spectral regularizer that I described. But similar ideas can be used for the structure sparsity. Right? There the matrix D will be diagonal, because you don't learn any directions. Right? So this requires further discussion, which I understood, which I skipped. What you can show, which is interesting, you can apply these methods, all these methods that we described, to a simple data set, which is available online, pretty much. You need to ask the permission of someone to use it. And you can see how the methods perform. So this is this data set of people and computers. It's a very simple data set, which is not really a real data set in the sense that all the people in the room, a bit more, are shown questionnaires. So they're not based on real life experience of the people, which could be people buying things in the internet for real, but they are given questionnaires and they have to fill up the answer about what they prefer. So it's kind of semi. So they're given questionnaires, and there are only 12 items that they need to rate between 0 and 10. So this is how much they like them, or likely purchase, they call it. And so 8 are used for training the model. So they have under 80 people, 8 training points per person, and 4 are used to test, to see how well it works. And here you see the test error, and you see that as the number of tasks increases, this is the average of the task, it goes down. So the more tasks you try to put into the, so this is exactly the previous problem. This one. So you improve your prediction. And if you look at this matrix D, which is alternatively found by this algorithm, which converges, you can show it converges. This matrix D has a very peak spectrum. And there is only one eigenvalue, which is very large. So this matrix is symmetric, semi-definite, so no need to speak of singular values. And then it's interesting to look at the corresponding eigenvector. Now the corresponding eigenvector, if you do all the computation, is exactly, so the eigenvectors of the matrix D will be the U, what previously I called the U, right, when I started from, right? So it will be the features. And if you look at the leading eigenvector, it has this shape, right? So these are the components, and you see that there is, the last component is very large, and these 3 are fairly large. And then you make a story. These people that do business make a story, which is that this is price, and these are the technical characteristics of the computers. So this is the most important features. People look at the price, and they compare it to the technical characteristics of the computers. This is a simple story which is made. So this means that now since the spectrum is like this, right, so what will happen is that most of the variance of the solution, right, so when you solve the problem, at the end you find this vector WT. So if you look at the variance, it's mostly concentrated on this direction, right? And it seems to be concentrated on 9-dimensional space, but maybe you can add here, so there are only 4 dimensions which are important. So there is an approximate low rank assumption here discovered by data. If you try the other methods, they don't work as well in this case. So first, if you learn the task independently, you do a ridge regression for each, you get a very bad result, right? If you aggregate them, you only learn one regression vector. They're all the same. You get this error, and then you can do the structure sparsity. It does much better. Then you can do the trace norm, which is this method that I described. You improve. Then you can start to do some engineering. So you try to combine things. You can further improve the results. Right? Even though if you keep trying things, at some point you will overfit the test set. So, right. Next 5 minutes, I'll tell you briefly. So, first, these things can be extended in using kernels. So the main idea is that all the methods that I described the underlying task functions are nonlinear, and you can relate them using kernels. I'll skip that. But what I discussed today, I think, is the most interesting part, perhaps. This is more interesting and is more complex model and the robustness of these methods. So here I describe very strong assumptions. So the first method, like, says that there is small variance, so you only one parameter which you can tune, which controls how much this variance is. The second, there is a common underlying sparsity. The third, there is a few common features, low rank. But so maybe the tasks are more heterogeneous. So maybe some people in the room, a group, look certain things on the computer, some other people look at other things. So then it's not correct to assume that there is a common. So you see what I'm saying, right? Or maybe there are some outliers. There are some tasks which are kind of random and they don't, they cannot describe like the other task by common structure, right? So you can, to some extent, relax the previous assumptions, and so there have been some works. So, for example, you can do this stuff. So you can say that the task matrix is equal, W is equal to a matrix V plus a matrix Z, where the matrix V satisfies the assumption, and the matrix Z is something which deviates from that. So it's like, right? So you allow that this matrix Z is sparse, right? So for example, it could be that in a sparse in a structured way, or it could be sparse across the columns, which means that few tasks deviate from the assumption, if you think about it, right? So WT is equal to VT plus ZT. Typically ZT is 0, which means that the assumption enforced on V is also enforced on W. But sometimes it's non-zero, maybe occasionally, which means that WT has a different configuration. So this is kind of. And then you can do other things which are skip. The first one is the most interesting mathematically, very general, is that you can do a composite regularizers. So you assume that there is structure, there is some answering machine. So you can assume that there is structure not on W, but on a linear transformation of W. So this B transpose W is a linear transformation. So W is a matrix. B is a linear operator, so it's a matrix. It's a very fat matrix, huge, right? So you see what I'm saying. But so let's skip this because we need to fulfill our schedule. So, I think this is enough. If you want, I want to. Yeah, so I think actually we can probably finish a little bit earlier. This is what the last thing I want to discuss. This is interesting. So this is interesting also because so this is a, so you can say this story in different ways. So one way is that there are some heterogeneous tasks. So the structures is involved across different dimensions. Very cryptic message. So here you assume that you have tasks of two types. So the first are tasks. This actually is a classification. So each task is a binary classifier. So the tasks of the first type are emotion recognition tasks. So the first task is to recognize happy face. The second is sad, surprise, etc. So overall, by the way, all these tasks is multi-class classification, if you think about it. Right? So right? So you can apply all these methods that I described also for multi-class classification. So I open a quick parenthesis, where the first task is to recognize one class versus the others. The second task is to recognize another class versus the others, and so on, right? So each classifier is associated to a vector, and you can put some common structure across these vectors, right? But so here I regard each of these vectors as a task, even though overall what I'm doing is just multi-class classification. So it's a bit of a subtle distinction. So if it's not clear, ignore what I said. So you have many tasks, each of which is binary classification. And the first group of tasks are emotion recognition tasks. The second group of tasks are identity recognition, right? So the reason is that there are different people in the database and different emotions. There's people. These are played emotions, so these are acted. As you can see, they don't look extremely real. So this is a data set from Japan, which some of my colleagues asked, but was in Japan at the time. So here the task is to, so as I discussed today, one way to do multitask learning is to find common features, so common representation. But here it seems reasonable to assume that those common features which are useful for emotion recognition are different or, for extent, opposite or orthogonal to the features which are important for identity recognition. But the reason is that identity of a person is more easily is well recognized by some geometric feature, like the distance between the eyes, or something which is something which is more rigid in the face, right? Whereas the emotion involves some deformation, which corner of the mouth or stuff like that. I don't know these things, so I just try to make a story. But I think it's quite intuitive, right? That, yeah, I think it's quite intuitive. So the distance between the eyes is invariant from the does not depend on the emotion displayed, whereas the emotion displayed, for example, the openness of the mouth, could indicate if the person is surprised, if he's happy. It's a bit simplistic, but so here what we did, this is the joint work, we tried to find these common features for the two different groups of tasks. This is quite simple. But here we tried to do the following. So we try to do the two groups. The two groups of tasks compete for features, right? So we want that. So the matrix W, the columns of the matrix W are the motion detectors, and the columns of the matrix V are the identity classifier, right? And we want these to be mutually orthogonal. That's what this term, or approximately. Right? So this term here is small when there is some orthogonality, right? Which means that the columns vectors of W live in a different space than the column vectors of V. So the idea is that you try to find two different subspaces, one for the first group, one for the second group, which there's a small angle between these two subspaces. That's the idea. So you can solve the problem. The problem is more complicated because this term is nasty, it's non-convex, it's difficult to, but you can still go to a local minima of the objective function, and the result seems encouraging. So I think the method is right. So this is the method that works the best. It looks good. Right. And I think I'll stop here. Maybe, yeah, I think we can stop here. for questions.